Hi, and welcome to more factoring day 2. Today we're talking about structures in graphs of polynomial functions. Or, what does the graph look like? Sketch the graph of f of x equals x squared. What will the graph of g of x equals x to the fourth look like? Sketch it on the same coordinate plane. What will the graph of h of x equals x to the sixth look like? Well, in order to get a more accurate picture of what we're doing here, I'm going to have every 2 be 1 on the x-axis. And I think I'm going to have every one of the y be 4. Okay, so now I have your x's labeled. I decided to do the y's by 4. So if I'm going to graph the f of x here, negative 1, x values negative, so it's negative 2, negative 1, 0, 1, and 2. If I put a negative 2 and I square it, I will get 4. If I put in a negative 1 and I square it, I get 1. If I put 0 and I square it, I get 0. 1 and 2 becomes 4. So my points are 0, 0, and then 1, 1 will go over here, and then 2, 4. Okay, then over here I'm going to have negative 1, 1, and then negative 2, 4. So this is f of x. The next graph I want to look at, but I'm going to change colors. So let's make it green. This would be g of x. Negative 2, negative 1, 0, 1, and 2. If I put negative 2 in and raise it to the fourth power, I will get 16. Negative 1 raised to the power is 1, 0, 1, positive 16. So let's graph this one. I have the point 0, 0, the point 1, negative 1, and negative 1, 1. And then I have 2 and 16. So this is 4, 8, 12, 16. 4, 8, 12, 16. So this would be g of x. And then I'm going to do h of x, and I'm going to change the color yet again. So I'm going to do h of x, negative 2, negative 1, 0, 1, and 2. And this time I'm going to do x to the 6, so negative 2 to the 6 is 64. 1, 0, 1, and 64. So I have 0, 0, not 2 points. And then, I don't think I'm going to get to 64 on here, am I? So here, 24, 28, 32, 36. Okay, so 64 is going to be really hard for me to get to. But it's going to have to go way up like this. Oh, go through this one. So that's h of x. Okay? So notice that for every increase in power, my graph got narrower. Okay, and I also want you to look at the end behaviors. What's happening to the ends of my graphs? So when I'm going in to the right and going to the left, what's happening with my graphs, the ends of my graphs? So just take note, maybe jot a few things down about what you notice, and then I want you to tell me something you notice about all the equations that you're given. So we're going to do the same thing, except now we're going to talk about the graph of x cubed, graph of x to the fifth, graph of x to the seventh. Same idea. So let's go back. Change our blue for our original function. And I'm going to do the same scaling. This will be 1, this will be 2, this will be 3, negative 1, negative 2, negative 3. And if each one of these is 4, that will be 12, negative 4, negative 12. And this is f of x. And so negative 1, or sorry, negative 2, negative 1, 0, 1, and 2. So if I put in negative 2 and x cubed, I will get negative 8. If I put it into negative 1 in, I get negative 1. 0 is 0, 1 is 1, 2 is 8. So at negative 2, I have negative 8. At this one, I have negative 1, negative 1. Then I have 0, 0. Then I have 1, negative 1, and 2, positive 8. So what's happening is this. So this is f of x. Go in, change it to green. This one's g of x, and this time we're raising everything to the fifth. Negative 2, negative 1, 0, 1, and 2. And when I put in negative 2, I get negative 32. Negative 1 is negative 1, 0, 0, 1, 1, 32. So I have 12, 16, 20, 24, 28, 32. And then I have negative 1, 1, 0, 0, 1, 1, and then 12, 16, 20, 24, 28, 32. So let's look at this graph. Green is g of x. And then for the last one, let's get our orange. And we'll do h of x. And for h of x, this is x to the 7th. So I'm doing 2, negative 1, 0, 1, and 2. If I plug in negative 2 to the 7th, I'll get negative 128. And then negative 1 will be negative 1, 0, 0, 1, 1, 2, 128. Well, I'm not going to be able to graph that one. But I know that these 3 points still remain the same. But at negative 2, it has to be really, 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 really steep. So and that is h of x. Alright, again, I want you to notice the difference between the graphs, what happens as my exponents increase. Look at my ending behavior. What's happening to x as x gets really big. What's happening to y as y gets really, or sorry, x gets really, really small. What's happening to y As x gets big, as x gets small. What's going on? What do you notice about all three of these equations? And also, what do you notice about the graphs themselves? All right, moving on. Consider the following function: f of x equals 2x to the fourth plus x to the third minus x squared plus 5x plus 3 with a mixture of odd and even degree terms. Predict whether its end behavior will look like the function in opening exercise or more like the functions from example 1. Graph f using the utility to check your prediction. Where we need to focus is right there on the first term, because that's my highest degree, like we've talked about before. So that is an even number, an even degree. So would it look more like the first problem I did or the second problem I did? And then use your graphing calculator to check your work. Actually graph it. Now for me, without looking at it, I see the highest power is 4. So that means that it's going to have end behavior that's similar. So when I threw this into the calculator, I got something along the lines of this. So it would look more like this would be the opening exercise. And then let's look at the other function. F of x equals 2x to the fifth, minus x to the fourth, minus 2x cubed, plus 4x squared, plus x plus 3. With a mixture of even and odd degree terms, predict whether its end behavior will be like the function of the opening exercises or more like the functions from example 1. Graph it. Well, I'm saying because this has an odd power, it's going to be more like the second problem we did. So when I graphed this, it looks something like that. So this one looks more like the example one. All right. Thinking back to our discussion of x-intercepts of graphs of polynomial functions from the previous lesson, sketch the graph of an even degree polynomial function that has no x-intercepts. Well, something doesn't have any x-intercepts, that means it doesn't cross the x-axis. So we have two possibilities. You can graph any x to the fourth, and it's going to look something like this or something like this, and neither one of those has x-intercepts. Similarly, can you sketch the graph of an odd degree polynomial function with no x-intercepts? Well, no, because with the odd ones, you have them always crossing the x-axis, because one side is up, one side is down for their end behavior. And we'll talk more about that in class. So no odd degree always has at least one x-intercept. Always, always, always. Can't change that little fact. That's one way we can tell if it's an odd degree or it's even degree. Exercise 2. The Center for Transportation Analysis, or CTA, studies all aspects of transportation in the United States, from energy and environmental concerns to safety and security challenges. A 1997 study compiled the following data of the fuel economy in miles per gallon of a car or light truck at various speeds measured in miles per hour. The data is compiled in the list below. Okay, so here we have a function, and what you need to do is plot this in your calculator. This would be L1 and this would be L2. So this would be your X values. This would be your Y values. And I don't expect you to be able to do this if you don't have a graphing calculator. And we haven't talked about that too much. Oh, sorry. So we would go to your Stat button. And you have to do number 1, which is edit. And you have to enter the data into your lists. And once you get all your data in again, you hit the stat button again, and you're going to arrow over to calc, and then do number 4, which is line regression. Looks like line regression, it's line regression, AX plus B. This will kind of give you a picture of what it's going to look like as far as regression line. And that's assuming that this is linear, which I did just assume that. Alright, hang on, let me just double check something. Yeah, forget I said this. My bad. We don't want to do a linear regression. What I want you to do is see here, sorry. I were to plot a picture of it. It's really hard because it's a bunch of points. And it seems like there's one up here, one there, 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 one there. And this is kind of what the graph looks like. It's kind of hard to tell, but it's not linear. So what we need to do is turn our stat plots on. I'm not sure if you know how to do that, but it's forget that second y equals stat plot on, and then you do zoom number 9, which is stat, but you might need to check your calculator because I think some of the newer calculators, the zoom stat is actually zoom 0, but I'm not 100% sure on that one. So that's what it's going to look like. Let's plot the data using the graph utility. Which variable is the independent variable? That's your x values. They're your independent variables. Y is your dependent. So then it says this data can be modeled by a polynomial function. Determine if the function that models this data would have an even or odd degree. Well, by looking at the picture here, it pretty much is doing this. And since they're both ending in the same direction, which is down, it would have to have an even degree. Is the leading coefficient of the polynomial that can use to model this data positive or negative? Well, we know when we get positives, they all open upward. But if we have a negative one, it opens downward. If you remember from graphing a parabola, if it's positive ax squared, positive x squared, it opens up. If it's a negative x squared, it opens down. List 2 possible reasons the data might have the shape that it does. Well, one is the faster you go, the more fuel is used. That's one possibility. And another is fuel economy. Improves up to a certain speed. And then
after you get going too fast, it starts to lose, um, you're not doing as well with your gas mileage. So it kind of starts to go the other way. So there is actually optimal speeds for which you should travel in your car. If you're not aware of that, if you drive too fast, you're going to burn up your fuel just as fast as if you drive it too slow. So I believe that is it for this day's note. Hope it wasn't as bad as last night's. Sorry about the jumble there with the graphing calculator. I was kind of lost in thought. All right. Well, we will see you later.